and my supervisor is Dr. Amin Hammad. My research topic is point cloud semantic segmentation of concrete surface defects using dynamic graph CNN. Let's start with introduction. Recently, LiDAR scanners are used for inspection of surface defects. Moreover, point cloud generated by LiDAR scanner can be used for deep learning with convolutional neural networks. Let's take a look at problem statement. There is a need for automated LiDAR-based surface defect inspection. Moreover, image-based computer vision has some limitation. For example, they are mostly defined for simple flat surfaces and may fail in analyzing complex geometry. Moreover, good lighting condition is one of the main issues that should be considered in these methods, and another shortcoming is the necessity of providing supplementary information, for example, camera lens information or focal length information. Although much work has been done for processing images using computer vision, research on machine learning methods for point cloud semantic segmentation is still in early stages. The objective of this paper is proposing an approach using the 3D semantic segmentation technique for detecting concrete surface defect, including cracks and spots. Let's move to the literature review. I want to explain a machine learning approach for semantic segmentation of point clouds. Point clouds dataset are typically transformed into images or 3D voxels in order to be used for deep learning purpose. Learning from point cloud dataset is easier than measures due to their simplicity and unified structure. However, the transformation to images result in massive data with unclear invariances. So what's dynamic graph CNN? Dynamic graph CNN is a deep neural network for object classification, part segmentation, and semantic segmentation of point clouds. It's originally designed to detect indoor building elements, and it can improve capturing local geometric functions as it creates a local neighboring graph and dynamically update the graph with the nearest neighbors after each layer of the network. Let's move to the methodology. LiDAR-based defect detection using dynamic CNN has 5 main steps. The first step is data collection using LiDAR. Sorry about this. The second step is annotation of point cloud data. The third step is data pre-processing the captured data set. And the fourth and fifth step dedicated to training, evaluation, and testing using the adaptive dynamic graph CNN. The first step is data collection. Point clouds collected from 4 reinforced concrete bridges in Montreal. This video shows a sample of captured point cloud data. As you see here, you can see the defects on the surface of the bridge. The geometric features of defect, especially the depths, play an important role in extracting useful features using the neural network. Moreover, position of the LiDAR scanner affect the visibility of the defect in the collected point cloud dataset. And finally, fine registration process result in having reliable dataset to fit the convolutional neural network. Let's take a look at LiDAR resolution and quality. In this paper, we used a Faro laser scanner which has the resolution of 1:1/32, and the quality, which is the number of times the scanner hit the same point for Faro laser scanner, was between 1 to 8 times. Different settings, including different number of stations, were used to scan each of the bridges. As you see in the table, 5 scans were captured, and different resolution, vertical field of view, horizontal field of view, and quality was used for the captured dataset. The scanning process is affected by several factors such as the battery capacity, performance limitation, weather condition, and traffic constraints. So in this regards, the field of view was reduced to avoid scanning irrelevant object in some of the scans. For example, as you see in this scan 1 and scan 2. The second step is annotation. The annotation process is done manually in Cloud Compare software. 2 types of major surface defects include crack and spalling are considered. Then the data set are split into 3 classes of crack, spalling, and no defect. And finally, the data set of a scan bridge categorized into 5 areas. Several rectangular segments are selected and cut from each scan of the bridge using the following consideration. The size of each site should be between 1 and 2.5 meters, and the number of points should not be less than 150,000 or more than 400,000 points. This is the figure of a segment in Cloud Computer software. This figure shows the annotation process. We cut different parts from the scan bridges, then we segment. We cut different areas from the scan bridges, and then we segment different parts from each area, and after that we annotate crack and exploit in each part. The third step is data pre-processing. In this step, we augment the data set to enlarge it. So the Philip data was added to the data set, and area 1, 2, 3 was used for training purpose. Area 4 was used for evaluation purpose, and the area 5 was used for testing, which dedicated around 20% of the whole data set. Number of segmented parts is 204, and number of points is around 53 million points. Let's take a look at testings. 3 cases defined based on different number of points of 8,000 to 12,000 for block and a size of 40 centimeter. Confusion matrix is used to describe the model performance. The best results show the detection recall for crack and exploits are around 55% and 89% respectively. And increasing the number of points from 8,000 to 12,000 improved crack detection recall from 55 to 58. However, this increase resulted in decreasing the spore recall from 89 to 87 and non-defect recall from 97 to 96. This is because sometimes increasing the number of points can cause overfitting the model. In this paper, the recall is assumed to be more relevant than precision, as the process of concrete surface inspection aims to minimize the chance of missing actual defect points, and this can be achieved by minimizing the false negative prediction of the model. This figure shows the test result from 3 samples of semantic segmentation. The first row shows the original segmented part. The second row shows the manual annotation. And the third row shows the result of adapted dynamic graph CNN. As you see in the figure, most of the cracks and exploits are detected in these 3 samples. Let's move to the conclusions. This paper proposes an approach using the 3D semantic segmentation of dynamic graph CNN. The prepared dataset includes 204 segmented parts from 4 scan concrete bridges in Montreal. The case study shows the usefulness and robustness of the proposed method in detecting concrete surface defect from 3D point cloud data. And the best results show the detection recall for cracks and exploits are 55% and 89% respectively. Future work will focus on enlarging the dataset. A larger dataset is expected to improve the learning process, resulting in better performance and accuracy of the model. Moreover, the proposed method can be applied to other types of concrete surface defects and other types of material surfaces. Thanks for your time and attention. I'm here if you have any question.
Thank you, Fardin. Now we have time for a few questions.